Welcome back. So we were talking about compression mechanisms as a way to deal with the fact that in a lot of distributed learning scenarios, our agents suffer from limitations of communication resources. We talk about certain examples of these communication mechanisms that enjoyed, let's say, this nice property that the total compression error was bounded by, let's say, the magnitude of the signal square, such that if our signal goes to 0, the compression error also goes to 0. So therefore, if we think of what we are communicating to be some form of a gradient, and we expect that to go to 0 as our learning algorithm converges, we also expect, therefore, the compression error to go to vanish, right? So, but in each round of training, there will be some error that is going to be detrimental to the convergence of our training algorithms. So here we want to understand the role of that compression error on the convergence of our training methods. In particular, we're going to do that in the context of SGD. Okay, but nothing stops us to actually study more advanced training methods, as we have talked about them in our previous lectures. But in this case, we just want to basically understand the main steps and main ideas. To this end, let's consider some compression mechanism that satisfies two properties. So the expected value of the compression is some a times x, where a is between 0 and 1. And when a is equal to 1, that means that my compression mechanism is unbiased. Okay? So that's one condition. Another condition is on the total compression error. I'm going to assume that the total compression error is, let's say, bounded by some b times norm of x squared. And b is basically something that is larger or equal to 0. So when b is equal to 0, that means that there is no compression error. So essentially, I'm communicating x with full precision. Okay, and all the examples we talked about so far are actually instances of this are instances that satisfy these two conditions. For instance, if I let a to be p and b to be 1 minus p, I'll get back random dropout. Okay, or let's say if I let a to be 1 and b to be d squared divided by k squared, I'll get the unbiased random sparsification. Okay, all right. So let's say that therefore we have a compression mechanism and we are integrating that with SGD, okay? And we want to see the impact on convergence, okay? So our method therefore is something like this. Instead of using the stochastic gradient, I'm using the compressed version of the stochastic gradient to update my parameter and go from WT to WT plus 1. And I'm also going to use some learning rate eta, okay? So let's consider the following key step for SGD with compression. So again, I'm assuming that our function is some general function, not necessarily convex, but it is L smooth. And thanks to L smoothness, we know that basically we can upper bound the function at any point with a quadratic function. And that was basically the key result we leveraged to initiate the analysis of training algorithms such as SGD and SGD with momentum, etc. Okay. So this is our first step. Okay. Now the next step is to basically utilize the update of our method to substitute the difference of the next parameter and the current one, and we would be we will arrive at this point. Okay, at this equation. Okay. All right. So previously we didn't have basically C of G. We had G itself. And we were able to leverage, let's say, the assumption on a stochastic Ferstor oracle, unbiasedness, and bounded variance, and then carry out the rest of the analysis. In this case, however, we have this compression mechanism that we have to deal with. Okay, so one way to deal is basically take the expectation with respect to the randomization inside our compression mechanism. Okay, and also the randomization with respect to the current batch, while we condition on the previous mini batches. Okay, so if we do this and use the fact that basically the expected value of our compression mechanism is A times X, we'll be able to arrive at this equation, okay? All right. So therefore now there are, let me go back. So there is this term that we have to deal with, okay? So this term is relatively simple. It's very similar to what we had in the proof of SGD, except that we have this addition factor of A, okay? But that's fine. But this third term is something that we have to deal with. So what we can do is to add and subtract G inside this norm square, and then expand the resultant quadratic form. Okay. So we do this expansion. Now we have a bunch of terms. Okay, that we can deal with each of them separately by leveraging, let's say, the assumption on the compression mechanism as well as the assumption on the stochastic first order oracle. Okay. So for instance, the first term on the right-hand side, especially this term, is bounded by our assumption that the total compression error is bounded by some constant B times the norm of the quantity we are compressing. In this case, the norm of the stochastic gradient. Okay. The third term can be handled as follows. So this is the third term. So we're going to add and subtract, let's say, A times G. Okay, and if we do this, and again use the fact that our compression mechanism satisfies this property, that is expected value is A times G, and also use the fact that the randomization in our compression method is independent of our choice of minibatch, we'll be able to arrive to this bar after some very basic algebraic manipulations. Okay, so that's the third term. How about the term in the middle, this term? Well, this is something we've seen before. Okay, so this is basically talking about the variance of our stochastic gradient. Okay, which again we had an assumption on that. So we assume that we have access to an unbiased stochastic first order oracle, which would imply that this term will be bounded by sigma square, or bound on the variance, as well as the norm of the true gradient square. Okay, so therefore, if we put all this result together, we'll be able to arrive at this equation, which is again very similar to what we had before for regular SGD, except that some constants are different. For instance, I have this like larger constant here. I have this constant here, which I didn't have before. Okay, but again, at a high level, the equation looks almost identical, which basically means that we can utilize what we did in the proof of SGD here as well to arrive at this convergence result, which basically says that the norm of the gradient, our notion of stationarity, is bounded by two terms that that hopefully go to 0 as I'm running the algorithm. Or if I choose a carefully chosen learning rate, I'll be able to control both of these terms, both of these error terms, such that I can establish a convergence result for my algorithm. Okay, and indeed that's the case with some differences. First of all, given that we have compression here, we actually need to use a smaller learning rate. In particular, our learning rate has to be bounded by this expression as opposed to 2 over L. Okay, so again, that basically is saying that every round you have higher error that comes from two sources. One source is due to the stochasticity in your estimation of the gradient, because we are using a stochastic gradient. Another one is due to the error that arises from compressing the stochastic gradient. So to control these error terms, I have to use an even smaller learning rate. Okay. Also, if I basically look at this term here, so the second terminal convergence error is something that depends on the variance of our stochastic first order oracle, which was sigma squared. now I have this extra factor of p. So I can define this to be some new variance, which is at least as large as the original variance due to the approximation of the true gradient. So therefore, what is happening therefore here is that we can think of, again, the composition of our original stochastic Fersor oracle and this randomized compression as a new stochastic Fersor oracle, which has some bias, but also has some variance, which is larger than before. And the variance is larger again due to the fact that we are using compression to reduce the precision. Therefore, we are suffering from more error in each round. Okay. Okay, and yeah, so again, what is this variance? For instance, for two examples of random dropout and unbiased randomized falsification, we can calculate this precisely. So for the random dropout case, this variance is something like 3 minus 2p times sigma square. So let's say that p is very small, let's say 0.1. That basically means that I only communicate on average 10% of the time. Therefore, the new variance is roughly 3 times the old variance. Okay. For unbiased randomized falsification, however, where a is equal to 1 and b is d squared divided by k squared, the new variance is actually significantly larger. So it actually goes up by a factor of d squared divided by k squared. Okay. So this again highlights the fact that bias estimators, bias compression mechanisms could be better than the unbiased one due to the fact that they have a significantly lower variance, which could be less detrimental, therefore, to our convergence results. Okay. All right, so another remark is that if I set A to be 1 and B equal to 0, I should get back the result we had before for SGD, because A equal to 1 and B equal to 0 means that I'm not compressing at all. And indeed, that will be the case. Okay, so we will get back to the result we had before for SGD. Okay, but what I want to highlight here is that, again, what's the order-wise? What's the convergence? So again, after certain and simple manipulations and approximation, we can basically show that the norm of the gradient square is bounded by, let's say, A inverse divided by the square root of t, when A is strictly less than 1, which means that we are using biased estimators or biased compression mechanisms, and B is also strictly less than 1, while our notion of convergence, the norm of the gradient square, is of order of B divided by the square root of t, when we are using unbiased compression mechanisms, which means that for them B is strictly larger than 1. Okay. So therefore, the idea is that for both of these cases, whether we are using bias or unbiased, we have some convergence rate. When in terms of the dependence on t, it actually has the same dependence compared to SGD without compression. Okay, so that's one good news. Another takeaway is that given that A inverse is typically significantly smaller than B, biased compression mechanisms are advantageous compared to the unbiased ones. But the catch here is that now the dominant term, which is basically 1 over the square root of t, is much worse because it depends on A inverse or B. Okay, so we have this dependence on the impact of on our choice of compression mechanisms when we look at the dominant term. Okay, and this is basically not very desirable, and we want to see whether there is a way to modify the SGD algorithm itself to make sure that there is no appearance of these parameters A or B on the dominant term of the convergence result. And indeed, the answer is yes. We can modify SGD in a very elegant way to almost get rid of the impact of compression. And that is basically something we're going to talk about in the next video. I'll see you there.